The video you're going to watch is an excerpt from a comprehensive 8-hour workshop that we have been running every year for the past 15 years at the Geopolymer camp. We have trained literally thousands of engineers from all over the world and from many different industries. A complete tutorial has been videotaped and is available for purchase on the Geopolymer Institute website, along with dozens of ready-to-use recipes and detailed procedures, and the latest edition of the Geopolymer textbook. A link is provided in the description below. Why is your geopolymer cement so wrong? Why can't you get the superior properties you read about everywhere? Professor Joseph Davidovits and I have decided to release this tutorial excerpt for free because there's still a problem today with those who want to make geopolymer cement that cures at room temperature. Those who make ceramic-like and other geopolymer binders are not concerned with this issue. It only focuses on geopolymer cement. Geopolymers are not alkali-activated materials. I need to develop this topic. I regularly meet people who are aware of this problem, and they say that they don't want to get involved in this controversy, or that they don't want to take a position because there is no clear consensus between these opposing concepts. But this is not an opinion. And you don't have to choose one side or the other. It is a major scientific error propagated by a small group of scientists. Let me prove it to you. For 15 years, a small group of experts nearly destroyed the concept of geopolymers by spreading misconceptions, bad knowledge, very poor and low quality results. It is a serious issue that has done a lot of damage to our scientific community. Misinformation can lead to disastrous outcomes when spread for years by a small group of academics in civil engineering. You will massively find them in the scientific literature, mainly between 2003 and 2019. However, I am glad to tell you that this ideological trend is now becoming a minority. Thankfully, companies and engineers all over the world did not follow them down this dead-end road. Some of these academics still refuse to acknowledge their failures and continue to promote a system they don't understand. This chapter will be helpful in recognizing them. What is a geopolymer? I will not repeat the definition given at the beginning of this tutorial, but bear in mind that some experts have no knowledge of polymer chemistry and are therefore unable to properly understand and develop a geopolymer formula. It is not alkali-activated compound. It is not alkali-activated metakaolin, no alkali-activated fly ash, no alkali-activated slag, no alkali-activated podzolane, no alkali-activated whatever. It is the geopolymerization of silicates and aluminosilicates in alkaline or acidic medium. There is no other definition than saying we are polymerizing, making a polymer with silicates and aluminosilicates. When they claim geopolymers as known as alkali activated materials. Let's compare the geopolymer process with how the others are doing. This is an example of a wrong mixing when some scientists have no understanding or no knowledge of polymer chemistry. Everything here is wrong. Now I suggest you go back to the 3 geopolymer formulations I showed you in the previous chapter. You can see a massive difference between our method and the order of mixing compared to that. Because each step has a purpose, each step is related to chemistry, and each step follows the kinetics of a polymer, not of a hydrate. Please note that I am not blaming this particular team in this video. They were faithfully following and copying what others were promoting. This is a true example of a wrong mixing we find in the scientific literature. It is neither alkali-activated materials nor geopolymer. It is rubbish. Don't be fooled. You will find many of these misleading papers. If you really understand the polymer chemistry, you will be able to tell the difference immediately. Let's explain why it's wrong. They mix the upcoming materials one after the other for several minutes. Fly ash, NaOH solution, sand, crushed stone dust, and sodium silicate solution. They start by dissolving the fly ash with a very corrosive NaOH solution following the alkali activated process. They mix a little to start the dissolution, then they add sand and crushed stone dust into the slurry. Problem number 1. They don't give enough time, only few minutes, for the NaOH to dissolve the fly ash, when it takes hours. Instead of attacking and dissolving fly ash, some NaOH covers the surface of the sand and crushed stones for no reason. As a result, some NaOH is removed from the fly ash dissolution, so there is less NaOH to react with fly ash. You know that sand and crushed stones are inert materials. NaOH will do nothing to these inert materials. It is useless here. Problem number 2. They read that geopolymers use sodium silicates, so let's add some silicates to go along with this new fashion. They add it at the end of the mix, playing the role of a simple fluidizing agent, bringing no reactivity at all. Because liquid NaOH already covers the surface of fly ash, of sand, and crushed stones. You know that NaOH and silicate, when mixed together, will produce a lot of heat, giving the impression that a strong chemical reaction is taking place, and we may believe that it is starting to harden. As a result, everything here is wrong. In the end, there will be a lot of unreacted NaOH and free silicate in the mix. This is because sodium is very soluble in water. It is not calcium hydrate, which is insoluble. And it will cause lots of blooming, efflorescence, cracking, shrinkage, and the like. No, this is pure rubbish. It is not alkali activated material, and it is not geopolymer. But in their papers, they use both words as synonyms. This is the result 1 month later, full of blooming and efflorescence of sodium salts. You will never get that if you strictly follow our procedures. Under the optical microscope, we compare on the top left Portland cement mortar and on the bottom right geopolymer cement. It seems like geopolymer cement is amorphous. It looks like a gel. No, it is a nanostructure instead. Some Portland cement scientists try to use their terminology to explain geopolymerization, which is completely wrong. Let me explain it to you. With Portland cement, they add water to clinker, providing a hydration reaction to form CSH. CSH is a small molecule. It's an oligomer. Here it's D-calcium silicate. It is not a polymer. For geopolymer, we have an oligomer of potassium oligosilate siloxo that polycondenses into a three-dimensional network polymer, potassium polysilate siloxo. We have the silate link, silica, oxygen, aluminate. Aluminate is aluminum salt with oxygen reacting with potassium or sodium. And we have the siloxo link, silica and oxygen. Silate and siloxo are always together, and oxygen is binding them together with the help of a potassium or sodium cation. You are now beginning to understand the chemical reaction. Cement scientists continue to explain geopolymerization with their Portland cement terminology. Here is the chemistry of Portland cement, which is correct. It's a calcium silicate hydrate, CSH. But they want to apply the same logic to geopolymer, which is wrong. Alkali activated material scientists want to substitute calcium with sodium or potassium. So they say that a geopolymer is either a sodium aluminosilicate hydrate instead of a calcium silicate hydrate, or a potassium aluminosilicate hydrate instead of calcium silicate hydrate. We know that calcium is not soluble in water. Calcium is a mineral. It is not a salt. But sodium and potassium are very soluble in water because they are salt. So a hydrate of sodium and potassium will yield to salt migration, which is logical, giving an unstable structure. Calcium is not a salt. It is a mineral, so it does not migrate. NASH or KASH are a wrong terminology for geopolymer cement. According to alkali activated materials specialists from RILEM, the RILEM is the International Union of Laboratories and Experts in Construction Materials. Geopolymer is a type of alkali alumina hydrate, a precipitate. NASH, KASH, nothing else. Wrong. It is confusing when someone claims that a mineral polymer shares similarities with a mineral hydrate or a mineral precipitate, pretending that they are all the same thing. This is a significant mistake. Polymer, hydrate, and precipitate are distinct chemical entities that cannot be everything at the same time. They are not synonyms. It is not called geohydrate or geoprecipitate. It is called geopolymer for a purpose. On previous slide, number 62, I have shown a simple test to prove that a geopolymer is not a hydrate when I talked about the water to binder ratio. If we compare the water to binder ratio, the addition of water in a geopolymer formulation implies a weakening of the material. When we double the amount of water in geopolymer, we go from 80 MPa to 3 MPa, compared to Portland cement, which goes from 70 MPa to 40 MPa. This is explained by the fact that the added water is not used to form a hydrate, as in Portland cement, and therefore does not participate in the structuration of the material. This is the proof that a geopolymer is not a hydrate. It is not NASH, sodium aluminosilicate hydrate, or KASH, potassium aluminosilicate hydrate, as some scientists keep calling it. Because water dilutes the chemicals. Adding more water in a geopolymer binder results in a sharp drop in performance. And what do other scientists say about this? A paper published in 2016 by the School of Civil Engineering at Shenzhen University in China provides a definitive answer, which has not yet been challenged by another team. They wanted to understand the role of water in a geopolymer exposed to high temperatures, and why geopolymer cements are fireproof when ordinary Portland cements explode. If the water exists in the form of a hydrate and contributes to the structure of the material, it should explode when exposed to fire. However, if the water is present as free water, meaning it is not in a hydrate form, steam can escape without causing damage to the structure. Let's read the abstract. This paper addresses the question of whether the main product of low calcium fly ash based geopolymer is a hydrate, namely sodium aluminosilicate hydrate, NASH? The answer to this question is important for understanding geopolymer characteristics. One of these is its fire resistance. In this study, fly ash geopolymers were synthesized. Then the samples were cured at ambient temperature for 7 days, then placed in the oven at 100 degrees Celsius for 24 hours, and then calcined at 1000 degrees for 48 hours. Infrared was used to examine the produced geopolymers at each stage so as to further knowledge on the following issues: the possibility of coexistence of calcium aluminosilicate hydrate, KASH, and NASH, the roles of cations as compensator and network modifier, as well as the role of water. The results obtained suggest that the primary geopolymerization products, which are potentially good fire resistant, are unlikely to contain hydrates. Even if there were hydrates, their amount must be very small, such that the escaping of water does not compromise the structure's integrity. I read some excerpt from the paper. Contrary to Davidovits's perception about geopolymer not being a hydrate, some researchers since 2005, Fernandez Jimenez, Palomo, and the like, have claimed that sodium geopolymer is a sodium aluminosilicate hydrate, NASH, meaning it's an alkali activated materials. This term, together with KASH, potassium aluminosilicate hydrate, or similar gels, was introduced by Fernandez Jimenez and Palomo in 2005. Prior to this, the understanding of geopolymeric product was not based on it being defined as a hydrate. It was considered as an aluminosilicate, as a polymer. Nevertheless, in those research papers, Fernandez Jimenez and Palomo, they considered the main product of geopolymer as a hydrate. Nevertheless, the concept NASH was widely accepted in the description of geopolymers. To understand the context, we add this comment, which led to its adoption by the RILEM Alkali Activated Materials Committee, in which these authors, Provis, Fondaventa, Jimenez, Palomo, were also members in this very committee, which raises the question of a potential conflict of interest. Davidovits, however, has clearly pointed out that a geopolymer is not a hydrate, and the term NASH is not correct to define a sodium geopolymer. Moreover, he called for an effort to be made to stop giving bad definition to geopolymers with non-proven facts. Yes, fake science. It is thus evident that the key argument relies on whether there is structural water in the geopolymeric product. Now let's read the last conclusion. The evidence obtained from infrared is not adequate to prove the existence of structural water, and the assumption that the main product of sodium geopolymer is NASH is not favored. The expression "is not favored" is a diplomatic way of saying that the NASH hypothesis is wrong. And remember that in their abstract, the authors left no doubt by stating geopolymerization products are unlikely to contain hydrates. Infrared proves that a geopolymer is not a hydrate. Alkali activated materials are not polymers. they cannot be called geopolymers. These are two very different systems. It is a big scientific mistake to use both as synonyms. Alkali activation is a wrong terminology for geopolymers. What is activation? It is the process of transforming a material from a stable state to an unstable state. You can change the state of a material by various means, such as calcination at high temperature or dry freezing at low temperature, acid attack, alkaline attack, mechanical process, high pressure, radiation, and so on. A reactive material is unstable and ready for a chemical reaction. For example, kaolinite is transformed into metakaolin by dehydroxylation, which is the process of calcining the material at 700 degrees. So, metakaolin is the unstable state of stable kaolinite. You don't activate metakaolin. You don't activate what is already activated. Fly ash and slag are also reactive by their very nature. If you really want to stick with this misleading terminology and claim that geopolymers are a subset of alkali activated materials, you must say that you create non-activated geopolymers. Non-activated geopolymers are not alkali activated materials. And alkali activated materials are hydrates. They are not polymers. Does that make sense? These are very basic concepts, but why is it that only a few academics in civil engineering refuse to learn them? Other engineers in the industry have no problem with polymer chemistry. Are there some other activators instead of NaOH? First, there is no geopolymer activator. There is a reagent, a reactive ingredient, or hardener, water glass, liquid silicate, sodium, potassium silicates, and we use alkali and acidic medium. Second, there is nothing to activate. Metakaolin is by nature super reactive. Glass in fly ash is easy to depolymerize. This is NASH, full of blooming and efflorescence of sodium salts. This is a hydrate of very soluble sodium that goes out. This is a polysilate siloxo geopolymer ceramic. Here is an interesting example from the Concrete Society in the United Kingdom. According to their website, geopolymeric cements are particular examples of alkali-activated pozzolanic cements or alkali-activated latent hydraulic cements. It must fit into one of their definitive and authoritative classifications. However, the polymer classification is missing from their list. And by giving two possibilities, being either a pozzolanic or a latent hydraulic cement, the geopolymer definition appears to be somewhat ambiguous leaving room for interpretation. So you have to make a choice regarding which category it falls under, because they don't know. In 2023, the Designing Buildings website, which is funded by several major building organizations in the United Kingdom again, makes a very interesting comment on the alkali activated materials page. The term and concept of geopolymer was developed more specifically by Joseph Davidowitz later in 1979. And with ongoing development in the field, definitions of what a geopolymer is have become gradually more diverse and at times somewhat conflicting. Definitions of what a geopolymer is have become gradually more diverse and at times somewhat conflicting. Finally, these UK official committees acknowledge that there is a problem with the definition of geopolymer cement and that alkali activated materials do not share the same category. Until now, there has been a limited understanding that it is indeed not a hydrate, but a true mineral polymer belonging to a new and distinct category within the realm of polymers. It is called geopolymer, not geohydrate. So these misleading definitions, supported by just a few renowned experts in cement, are doing a lot of harm, fooling scientists who blindly trust and faithfully follow them. Fortunately, you see that this deceptive language is now losing popularity. There is still a minority who refuse to admit their mistakes, but most engineers understand the true logic behind the geopolymer concept. It is with this technology, the polymer chemistry applied with proper knowledge, that gives customers the confidence to invest in a major project, such as this first public building using geopolymer cement at Brisbane, Australia. This was followed by the construction of an entirely new airport, including the terminal building and taxiways, using 100,000 tons of geopolymer concrete in Australia. Finally, when engineers have a good understanding of true geopolymer systems, they can develop innovative processes with highly complex formulations. They were able to 3D print the first geopolymer cement house in Las Vegas in the USA in 2023.